Hello everyone, my name is Triswan for the group number 16. Today I'm going to present about the battery power DC to DC converter via presentation. Our outline will be the project specifications and objective, converter main components, operating principles, component sizing methodologies, final component selections. This topic will be presented by me and the remaining will be presented by my other group members. Okay, our specifications are the 10-volt battery, then output range from the 5 to 20 volt with the 10 ohm resistor. We use the 2 kilohertz switching frequency. The output voltage ripple must be equal or less than plus or minus 5%. We're going to use the CCM, and our objective is to make a design and simulate the converter and to implement two control strategies. And also we compare their performance results. And also we make the interface from the circuit to the dashboard for the real-time testing. Why this converter? Because there's a lot of advantages. They are the single topology and also simple structure. Output voltage can be the higher or lower than the input. Ideal for the battery power portable system. There are a lot of application for this the converter, such as the battery power devices, negative voltage supplies, and automated system, and portable electronic devices. Okay, main components are 10-volt battery, MOSFET, diode, inductor, output capacitor, load resistor. Then operating principle is for the inverting buck boost converter operating in the CCM, continuous condition mode, the relationship between input voltage and output voltage. The duty cycle is calculated by the equation. We get about 0.33 for the buck mode, 0.66 for the boost mode, and 0.5 for the nominal mode. Okay, the next for the sizing the component. In data sizings, as per the calculation, we get over 416.7 microhenry. Then we do for the CCM condition, we get the 111 microhenry. Then we multiply with 2, we select that as the 220 microhenry for the inductor sizing. The next for the capacitor sizing. According to the calculation, the both mood must be equal or more than 66.7 microfarad. For the safety margin, we multiply with 5. We select the weight 330 microfarad for capacitor. All right, the final component summary. So we can see in the tabulated table, inductor sizing is about 220 microhenry, and the capacitor is for the 330 microfarad. Thank you very much. The remaining slide will be presented by NC. Bye.
Good afternoon, my name is NC and I will present our control system design, simulate dashboard and step response result. We implemented two discrete time control strategy at 20 kHz sampling. Method 1 is a single loop PI voltage controller. Method 2 is a cascaded PI controller with inner current loop. Method 1 uses a single loop discrete PI controller. This method is simple. It uses the voltage error to directly calculate the PWM duty cycle. We tune the proportional indicator gain to make it work well. It is P equals 0.05 and I equals 10. We also scale the error down by 1/4 so the controller wouldn't react too aggressively. Finally, we limited the duty cycle between 0.1 and 0.9 to keep the circuit stable. Method 2 is the cascaded PN controller. This method uses two loops. The outer voltage loop P equal 1.2, I equal 100 generate a current reference. This is situated at 10 ampere for safety. The inner current loop P equal 1.2, I equal 1200 regulate inductor current and produce the final duty cycle. This structure provides faster disturbance rejection and lower overshoot. We implemented a unified dashboard with parallel architecture, running both controllers simultaneously for direct comparison. A rotary knob adjusts reference voltage from 5 to 20 volts in real time. The dashboard includes integrated scope showing both output overlay. We also added screen to show the live numeric display of voltage and current. There is a pass and fill LED light too. It stays green as long as the voltage ripple stay under our 5% limit. Now let's look at our step down result. When stepping down from 10 volts to 5 volts, method 1 reached the target with moderate overshoot and a longer settling time. Method 2 demonstrates significantly faster settling time with reduced overshoot, highlighting the effectiveness of the inner current loop. Both controllers maintain ripple within plus or minus 5% specification. What you are seeing now is the step-down simulation running live on Simulink. The reference voltage is stepping down from 10 volt to 5 volt, and you can clearly observe how each controller responds to this change. We are now executing the step-up simulation using Simulink. In this test, the reference voltage is step up from 10 volt to 20 volts. This allows us to evaluate the performance of both controllers under a sudden increase in load demand. Finally, our step-up result from 10 to 20 volts. Method 1 reached 20 volts slightly faster, but exhibit noticeable voltage overshoot during transition. Method 2 has a slightly slower response but achieved the target with superior stability and minimal overshoot. Again, both controllers maintain ripple within plus or minus 5% specification. Now I will hand over to our team member Mintin T for the comparative analysis and conclusion.
Hello everyone, I am Balu Mahesh. I will talk about the performance summary in this slide. To the left we have Simulink results for method 1, which is PI control. It is simple implementation when compared to the method 2, but we observed high overshoot in both modes and slower settling time in especially buck mode, whereas the cascade control shown consistent performance across all operating ranges with less overshoot in both modes, and had a significantly faster settling time in buck mode with a good ripple rejection. Moving on, in this slide we will establish the pros and cons of the two control methods. PI control has poor ripple rejection, no overcurrent protection, slow response, making it less robust to method 2's current limiting faster settling time and lower overshoot in buck modes. Method 2 takes 63% less time than method 1 for the output voltage to stabilize after a disturbance. Advantages of cascade control. By adding an inner current loop, we are limiting the inductor's charging and ensuring the capacitor only receives exactly the amount of energy it needs to reach the target voltage. We prevent voltage overshoot by this way. Method 2 provides faster rejection as shown by its uniform performance. No additional power protection circuit is needed. The system maintains a stable margin at its operating range. We conclude the presentation by verifying and stating that we successfully implemented the inverting buck boost converter. With components selected with proper margins, CCM is operational at all operating range for this project. Ripple is maintained well within plus or minus 5% of the output voltage with 63% faster settling time in buck mode and better ripple rejection. We conclude that the cascade controller is preferred system for high performance in buck boost converters. These are the references for this project. With this, we conclude this presentation. Thank you for your time.